So here we are on question 5. Calculate the energy available from burning the propane contained in a 5-pound tank. The thermochemical equation is listed below and it's balanced. And then it says the molecular mass of propane is, and the conversion between pounds and grams is given right here as well. So step number 1, convert to moles, but before we can convert to moles, we've got to get 5 pounds into grams, and then we can go from grams into moles. So start way over here on the left-hand side with 5 pounds of propane, 5 lbs, and in 1 pound we have 453.6 grams, so the pounds cancel with the pounds. And then we can go from grams to moles. So put grams in a position where it's going to cancel, in moles of our propane, Ch5-6 on the top. And in 1 mole, it tells us there's 44.10 grams. So our grams will cancel with our grams. Then we can use the thermochemical equation, and we can relate moles of propane to energy that's released. And in 1 mole of Ch5, there are 2,220.1 kilojoules of energy released. Notice it's a minus sign right there because that's energy that's released. Multiplying these guys together and dividing and then multiplying again, we end up with 114,176, or rounding to 4 sig figs, 114,200, and that would be in kilojoules. So the link right here, remember, is the stoichiometric relationship between the energy right here and the 1 in front of the Ch5. Second question, that's similar to that. Calculate the heat released when 15 grams of C2H4 burns in an excess of O2 in the reaction below. And once again, we're given a balanced thermochemical equation. So step number 1, convert to moles. Now we have 15 grams of this C2H4, multiply sign, put a line. Put grams of C2H4 down here and put moles of C2H4 as your new set of units. And in 1 mole, you add up C2H4. Carbon, of course, is 12 times 2 plus 4 more for hydrogen gives you 28 grams. And then we can use the relationship from the thermochemical equation. And in 1 mole of C2H4, there are 1040 kilojoules of energy that are released. See this minus sign right here? Divide those two, multiply by 1040, and we end up with a negative sign, 557.1 kilojoules of energy, and of course that's energy that is released. I believe this should have a minus sign on it as well because it is energy that's released, because there's a minus sign right here, so it should be a negative amount of kilojoules, meaning that it is exothermic because it's energy that is available or given off to the surroundings. All right, question 6 on the next page. The top part is canceled off, but you actually use the answer from letter A right here to answer B and C. And so I've copied the answer right here, but there's no expectation that you'd have to be able to do a question like letter A. It would probably just tell you this is an amount of energy that's emitted or an amount of energy that's needed to move an electron from one place to the other. And then this is the type of thing that happens when you do a flame test, or like we did a spectrum analysis of different colors that are emitted when we burned or added energy to various metals. We moved those electrons, and then this amount of energy was added and then released, and then this would correspond sometimes to a wavelength that we could actually view. So what is the wavelength of the photon emitted in this process in nanometers? Hint, looked at the spectrum chart. So you could use the spectrum chart, and then you could just convert this energy right here to from joules to a usable wavelength, and then the answer from the spectrum chart should be reasonable enough. We'll do the math as well, but we have energy in joules right here of about 2 times 10 to the negative 18th. So here's times 10 to the negative 18th. 2 would be a little bit larger than this. Follow it up right here, and we'd be pretty close to 100 nanometers. It looks like it's a little bit bigger than that, so maybe 200, 300. We'd be in the order of somewhere between 100 and 1,000 nanometers, something like that. So let's do the math to find out what the wavelength would be again, and you can use the equations that are given to you from the front page of the test. and we know that the equation to find the energy is equal to hc over lambda. And then if we want to solve for lambda, of course, we can rearrange this, and it ends up being lambda is equal to hc divided by E. Well, we have E right here, so we can put the energy in, and then H and C, of course, are multiplied for us and given to us right on the front part of the test. So right here is HC multiplied together. Here's our E equals HC over lambda equation. And so H times C is 1.9865 times 10 to the negative 25th joules times meters. And then the energy that we're putting in here is 1.938 times 10 to the negative 18th, and that's in joules. The joules cancel with the joules, and we'll end up with a wavelength in meters. So when you divide those two, we end up with a wavelength of 1.025 times 10 to the negative 7th meters. And of course we want to get this in nanometers, because then we could just compare it to our 100 to 1,000 in here. And of course, meters to nanometers, in 1 meter there are 10 to the 9th nanometers. Whoops, nms right there. And so then add those two exponents and you end up with positive 2. So we'd end up with about 102 nanometers. And we said that we'd be pretty close to 100. And yeah, we're pretty close right there. And if we want to know which region of the spectrum this is, we want to find out about where 100 nanometers is. Notice that high energy right here is 380 nanometers. And so this low energy is about 700 nanometers. So we're a little smaller than that. We're about 100 nanometers. So we'd be in the ultraviolet radiation area, or UV right here. And you need a chart like this to answer that question. You do not need to memorize the chart, but you'd be able to interpret the chart that way.